Okay, so welcome back for the fifth and the last lecture of the series by Whaley.
Okay, thank you very much. So I'll continue from where we left before the lunch. So before the lunch, we finished with the description for this class of the quiver compound Torrey-Clavier. We finished the description of the BPS states in terms of crystals. And then I explained that the strategy, so I already defined the algebra, but here I want to explain how we actually defined it by considering the action on the BPS states. So remember the fusion is fusing more generally to arbitrary state, but this is very hard to manage. So instead we consider a special fusion process where one state is some unit state. So then we want to realize this fusion process by considering this part to be an action of the algebra. This is a so-called spherical part. So in this logic, the BPS Hilbert space will be a representation of the algebra that you want to construct. And then this action, so then we define the racing operator to be some operator that can add atom to any crystal, and also the Cartan generators, and also the lowering operator to be the action that remove atom from the crystal. And then we want to fix the action by demanding that they mimic the fusion process. So essentially we have two conditions. One is a cyclic condition. That means that you start from any arbitrary state and then you can reach any other state. And also it has to implement this adding rule that we explained earlier. So we want to define the action so that this condition are realized automatically. So for this class, so we see that for this class you have periodic quiver, so it's infinite, and then we will lift to the atom. Your Hilbert space is infinite dimensional. So for this, you allow it's possible to fix this. So once you fix the action, you can from there you can obtain the relations between this all the relations between these generators. So for this class of infinite dimensional representation, it's possible to just consider this vacuum representation to fix all the relations. And so for other quiver where you might have finite dimensional representation, then you need to consider all the possible non-vacuum representations in order to fix all the relations. And then the BPS algebra is just given by the free algebra generated by these operators and then divided by the relations. Right. So here a priori is infinite dimensional. So that means that we also have label. Right? And remember, we want to organize them in terms of this field. So now, a priori, I don't fix the range of this summation yet. This can also be fixed by considering the action on the representations. Okay. So now we write down the answers. So for any state, we want this state to be an eigenfunction of all the Cartans. So this is the eigenvalue function. And then applying this racing operator on the K, we want to add an atom of, so E of color A, we want to add an atom of color A on all possible places. And the pole here is given by the equivalent weight of this atom that you're about to add. And then similarly, the action of the lowering operator is that it's supposed to remove an atom of color A from all the possible places. So this is some coefficients here. So now we want to impose this. We want to fix this these three functions so that these two conditions are automatically satisfied. So we want to refine this ansatz a bit further. So this eigenvalue function takes on factorized form. So it has a contribution from the ground state. And then for each atom in okay, so so this is the cation for the of the color A. So it gets contribution from the atom of all the colors. And then for each color, you look at all the atoms of this color inside this K, and then it contributes the contribution to this eigenvalue is captured by a relative function. So it's a rational function, and then it's shifted by the weight of this atom economy. So is this notation in here? So this is function that this is the ansatz, and we need to fix this rational function. And so this is also ansatz. So there's some science that's also necessary, but we will explain that. So this is still an ansatz because we still. So, but now it boils down only to these two functions that you have to fix. So I just tell you the result. So so this is a so the result is that this one actually depends on the framing. So for the framing that we're considering, let's call this free vortex A hat, and A hat is inside Q. So this is the so this rational function is the bounding factor that I introduced on Tuesday. So the result is that so you have a quiver, and inside the quiver, for each arrow going from B to A, so this is the bounding factor from B to A. So for each arrow going from B to A, you get a factor in the numerator, and for each arrow from B to A to B, you get a factor in the numerator. So this is the result. So then you can check. You can try to convince yourself that with this solution, that ansatz will automatically satisfy the two conditions. So the scientific condition means that it gives you all the possible poles for you to add all the necessary poles so that you can cover all the states. And then remember we have the loop constraint. So with the loop constraint imposed, this also makes sure that there's no redundant poles. Meaning that you start from a crystal state. If you implement this, you won't get any final states that's not also a crystal. So I mean, all this is supposed to be automatic. So let me show you an example to convince to show you that how this works. So so the system is too simple. Let me show this example. So this is the Z2 orbifold, where the orbifold action only acts on the first two directions. This is the toric diagram, and this is the quiver. And this is the superpotential. So the periodic quiver is similar to the one we drew earlier for the C3. It just has this orbifold action, so that so it has the orbifold action along.
The potential doesn't have Steven dependence at all.
Sorry, I didn't.
Oh, it has. Okay, fine. There's a summation.
Yes, it's summation here. So this is 0. So so if you draw this, it's very similar to the one.
Some identification, right? BA plus B2 will be B0.
Yes. So this Z2 action acts on the first and the second direction. So along this two directions, the color will alternate. So you have 0, 1, 0, 1, 0, 1. And then along this the third direction, the color doesn't change. So now for this example, let's write down these ingredients explicitly. So we want to consider the case of the non-commutative chamber. So let's have this add framing vortex. and then it has one arrow that going from the framing vertex to 0. So now we just look at this and then plug in this. Sorry. So I also have to assign all these arrows some weight. So AI is H1, AI is H2, CI has weight H3. And then the loop constraint, so here you have H1, H2, H3. You see that, so this is a loop. So all the loop constraints are the same. Give you H1 plus H2 plus 3 equal to 0. So now, this is the same as this case. And 1 to 1 is also the same as 5, 0.
Excuse me, can you repeat how these directions are related to the quiver class? Because I'm trying to match this. There is H1, H2, H3, and this is AI, BI, CI.
Right, so okay. So this is A0, A1,
Okay.
and this is B0, B1. This is C0, C1.
Okay, so A0, then we go back with B1 and C0.
1. And this direction is H2. And this direction is H3. Any other questions?
Okay, now I see it.
Yeah, I forgot to mention that. So this is the loop constraint. So this corresponds to the global symmetries. So you can also impose for the general case. You can also impose the vertex constraint, meaning that for vertex, all the arrows going in for each vertex. The sum of the weight for the arrows going in is equal to the sum of the weight for the arrows going out. So this will correspond to gauge symmetry. So once you impose both the loop constraint and the vertex constraint, so you can check that for this class of quiver, you always end up just 2 independent parameters. So for any Tory club, yeah. So this will correspond to the fact that there's only 2 equivariant parameters for the Tory club, yeah. But in this case, it's very simple because you see that for the vertex constraint, it's also it's the same. Give it the same constraint as the loop constraint. Maybe I shouldn't. Okay, that's enough. That part is enough. So okay, let's start from the vacuum and then see how we build this build the states one by one. So this is the vacuum. So we apply all this the catons on this vacuum, and So it only has the first, only has the contribution from the ground state. So that means it's Z. So for the color, for the color 0, there's one pole at the Z equal to 0. So this will correspond to the pole where you can add the first atom. So I give you the states where you have the first atom. You see, then you use up this pole at 0. So that means that if you apply the lowering operator, this is 0. So that means that if you start from the vacuum, you apply the lowering operator, you annihilate the vacuum. And then for the color 1, there's just no pole at all. So that means this phi is a vacuum, means that it's vacuum. Okay, so we're good at this level. So now this the one state at level 1. So now we start from this state. So let's keep this. So now let's take this as the initial state. So the eigenvalue function for this state, you just take this and then you multiply by a factor from the bounding factor. So this again, we have the vacuum contribution. And this. So this is the atom that corresponds to this box here. So this would be Z. So this function here is this one, and then this weight is 0. So it's the same here. So now the bounding factor is the 1 from 0 to 1. So we're looking at this one here. So now let's look at the poles. So here we still have this pole. So for the color 0, we have the pole at Z equal to 0. So this would now correspond to the pole where you can remove this state. So if you apply the lowering operator, then you go back to the vacuum. Okay, and then this pole here. This will correspond to the position where you can add an atom at with the weight H3. So that means this second box here. So this is a new box here. I want blue. Okay, so now for the color 1. So we have 2 poles here. So this will correspond to the 2 places where you can add an atom of color 1. So there are 2. So this one has the weight H1, and this one has the weight H2. So it gets interesting at the next level. So this is so at this level you don't see the adding rule yet. So now let's consider the initial state. Let's consider this this initial state. Then you want to compute the eigenvalue function of this initial state. So we have z, and we just start from here and then multiply the contribution from this new box here. So I won't. So now I have the contribution from color 1 to this. So the weight of this new atom is H1. So that means it's Z. So now they start to have cancellation. So remember this pole here, this z equal to 0, means that it's the pole where you can use the lowering operator to remove this. So now once you add this one, so you see that there's this 0 cancels this pole. So you're losing this pole. So that means that once you have the second that means that once you have this new atom here, you can't remove the one at origin. So that makes sense. And now this pole here, that's still there. So that's a pole where you can add. Right. So this is the pole is still there. So that this is the pole that corresponds to where you can use this E1 to add a box here. And now let's see what are these 2 poles. So this is all about the E1 or F1. So this will correspond to a box that you can put here, which weighs 2H1. And this, you see that with the loop constraint, this cancels this. So if this one is not doesn't get cancelled, you would have been able to add a box at this position. But because this pole get cancelled by this, so that means that you can't add this one here. But this is precisely agree with the adding rule, because according to the adding rule, so let me draw it just a projection here. So if you want to add a box here, you need both these two to be present because there's two precursors here. So now if I have this one, you only have one precursor here. So that corresponds to the fact that this pole is just not there. So now let's check that once we have both precursor present, then you have the necessary pole in order to add this box here. So that means that we want to start with this initial state. So this is the function for this is the eigenvalue function for this part. So this new one gives us the contribution here. This is the pole at with a weight h2. So this will have a z. So you see, this new factor will again provide this pole that you can use to add this box, and this one corresponds to the place where you can have a box along this x2 direction. So this one has 2h2 weight. Yeah, so this is how it works. So you see that as you add more and more boxes, the poles always get pushed to the surface. So then, so you will lose the poles that so the poles that correspond to the older atom got buried inside, so you can't remove them, and then you can only you only have the poles that near the surface where you can add the atom or remove the atom. So everything just happens near the surface. So this is all automatic. So now we fix the action. I wrote down the action here. It was used to be here, and then this with this ansatz, and with this binding factor given by some definition I wrote earlier. So this will be the most important ingredients of the algebra. So this will enter the algebra, and then this part will capture the information of the framing. So so now you can check that so we fix the action of a single generators. So now you just apply two generators to find the quadratic relation between all these generators. You just apply one and then another one, and then you reverse order and you compare. So that will just give you the quadratic relation that I wrote down on Tuesday. So that will be universal, and only this binding factor enters the definition, and then some signs that haven't fixed here. So you see that from this, yeah, I erased all this already. So from the action, you can also fix the range in the mode expansion. So there you can see that in this expansion for the f and the e, the j take only the non-negative integers. And then for the precise, you can try to convince yourself that this will depend on the type of quiver. So for the Club 3 without first cycle, without compact first cycle. The quiver will be symmetric. So that means that this mode expansion is bounded from below. So, and for the toric labial 3 with the compact first cycle, this will be non-symmetric. And then, so this is, you take the mode expansion have to run from all integers. Okay. So now you just apply this operator for multiple times, and use that to fix the higher order relations. And you know that you get all the relations after the character of this algebra reproduce the crystal counting. So the last thing I want to mention is that so this is we fix this the algebra by just looking at this non-commuted DT chamber. So that corresponds to this factor. So that means your first at first order, there's only one state that's given by this pole at 0. Pole of z equal to 0 at color a equal to a hat. A hat is the frame vortex. So now, how about the other framing? So suppose you have, so this is the framing vortex. Suppose you have more than one arrows going in and some arrows going back. So for the arrow going in, you have a pole where the pole is at the weight of these arrows. And for each arrow going back, you have a numerator for this the contribution from the ground state. So this will allow you to consider non-vacuum representations. So this will give you not just other chambers. It will also allow you to define the. So you can have the open BPS counting. For example, for the C3 case, you can introduce the D2 brain wrapping on a disk of some D4 wrapping on a Lagrangian submanifold of the C3. So that will give us the. So we know that the open BPS counting for this case is given by the plane partition with the asymptotic given by the 3 Young diagrams along the. So now the plane. So the plane partition before, I didn't emphasize that the alternate plane partition has the trivial asymptotics. So now you can also have a non-trivial symptotics which is fixed, given by this Young diagrams. So that means that you take this Young diagram and then you look at the minimal configuration where with this 3 Young diagram as a symptotic direction. And so that minimal configuration will be the ground state of this representation. And then from there, I can add more boxes. So to translate into this framing, you just have to see where you can add a leading box. And so for each, it's hard to explain with this 3-dimensional space. So if you look at this way. So suppose I have these 2 positions to start my going my crystal. So now I have 2 crystals, 2 positive crystals. Then they will meet at here. So if I don't do anything, I will have overcounting at this part. So you see, this part is another full crystal that I need to remove. So that means that when they meet, that will correspond to an 0 in this rational function that corresponds to the ground state contribution. The upshot is that with this technique, you can define all the non-vacuum representation just by changing this factor. And then you see that when I want to count and then all the argument just follow through. So the only thing you need to change is here. It doesn't touch the algebra part. It only touches the representation. So the representation, different representations given by non-trivial framing. I think I want to say something about the
Please keep it.
Huh?
I haven't made a photo yet.
So Daniel asked me about this resolve conical case. So then so the quiver for that is this: A1, A2, A1, B1, B2, 0 and 1. B1, B1, B2, B2, minus B1, B2. So the periodic quiver is this square one. 0. This is this square lattice. And then if you grow the full crystal, if you uplift this periodic quiver, you get this pyramid partition function. So this will correspond to the non-committed DT chamber here. So this is the canonical framing here. So now, to go to the other chamber, you just mutate this quiver. And then the next one would be so you mutate once, you get this this quiver. So you see that this one has two it has two ingoing errors, and then it has two errors going from the frame vertex, and then one error going back. So that means that the leading position, you have two items here, and then so you see that you're adding these two crystals together, and then you have this overcounting. If you don't do anything here, then you double count. So that means that you have to have a you have to add a negative crystal here to remove this double counting. So this precisely corresponds to this error that goes back that provided 0 here. So then this will give you this pyramid with this edge here. So then if you just mutate step by step, arbitrary chamber would have m arrows going in and m minus 1 arrow going back. So, but to reach the topological string chamber, you see that you will have to mutate infinite many times. So all this finite, all this chamber that's away from the original DT, non-permitted DT chamber, by a finite steps of mutation, you can describe them as some non-vacuum representation that's given by this framing. But then, if you want to describe the chamber that's topological string, it's an infinite number, infinite. You have to have infinite number of factors in this the ground state contribution. So that becomes unwieldy. So what do you do there? So that's actually leads to another basis for this type of algebra. So remember that the starting point here is that I start from the toric diagram. So I first go to the quiver and the potential, and then I uplift to get a periodic quiver. So remember for the C3 case, so this would be a plane partition. And then from the plane partition, so this plane partition is, has just one color. And to generalize to the generic toric labial, so first you have more colors. And then the shape also change. It's not necessarily the plane. It's not necessarily plane partition. For example, this one has 2 colors, and then the shape is this pyramid, with 4 directions. So this is one way to generalize from the C3 to arbitrary toric labial 3. So actually, before this work, we actually tried a different way of generalizing to arbitrary labial 3, which is that we don't go through this route. We look at the dual diagram of the toric diagram, the one that corresponds to the PQ web. For example, for this resolved conifold, that's like this. So remember, if you focus on this piece or this piece, so they both correspond to a C3 part. So this suggests that the algebra you want to build has 2 sub-algebras. So one sitting here and one sitting here. So for the C3, the algebra is called alpha yang yang G1. Which I mentioned, I think in the second lecture, that this is isomorphic to the universal invariant algebra of W1 plus infinity. So that means that in this basis, we can see explicitly that this algebra that we want to find has 2 sub-algebras. So then you know the sub-algebras. So then you need to glue them here. So to glue them, you have this infinite leg. So that means that for this leg, you want to introduce some generators that add a row of boxes here. So you just need to introduce the gluing operator that transform as a bimodule with respect to these 2 sub-algebras. So using the same argument of this this bootstrap technique, you fix the action of this these 2 sub-algebra, the action on these 2 corners, they are fixed. You just need to fix the action of the new gluing operator that you introduce, and also you fix the mutual, the consistency condition, that you fix the interaction between this new operator with the existing operator. So after you fix that action, then you can bootstrap the algebra in this basis. So this will be the algebra, that will be the basis that's more amicable to the topological string chamber. Yeah, sorry. Any questions? I know.
Any references that we can go back and look at?
Yeah, so yeah, this comes from a series paper, I think, starting from yeah, it started from some earlier work, but you can look at two papers, one 1905, one 1910. So this one is with Pietro Longhi. So an earlier paper is we only studied this case. In this one, we studied more systematically of the two vertices with we start with two vertices and also what's the what are all the possible way to glue them. So if you impose the Clavier conditions, it's actually only these two possible ways. It's actually quite surprisingly tight, the structure. So this will correspond to the resolved conifold. This will correspond to the this case that I explained earlier. So one is the alpha Yang GL1/1, and this one corresponds to the alpha Yang GL2. So here this additional operator that you gluing operator you introduce are fermionic, and here this is bosonic. So this is like the gluing the topological vertex together. I mean, in some sense, this is so this is not a very efficient technique to generalize to arbitrary Clavier, but and also the computation is more complicated. But it can give you the confidence that this the gluing this bootstrapping technique actually works. Actually, it's quite non-trivial that this additional operator is the consistent condition of the new operators you add have to work well with the existing ones. So now you don't have different colors. You just have different shapes. So you generalize the C3 in a different way.
I have another question. Does the connection with not quiver correspondence go via this resolved conifold construction?
I'm not sure. I mean, the one I made it to work is to go directly from the quiver. But I think it would be interesting to see whether it will also connect this way. I mean, this is something that, yeah, I probably shouldn't say much, but this is something I discussed with Pietro and the other Pietro, and we can talk more about this.
Okay.
So the gluing can move you to one of the finite chambers that they're not.
No, I think the gluing, for the finite chamber, I think it's easier to capture via these mutation steps, and then all this is just given by this the rational factor that capture the ground state contribution. If it's finite, I think there's no point using the gluing. I think this gluing is more amicable for the yeah. I mean, you can also say that okay, I start from this end, and then I can mutate. I can go starting from the topological string chamber and backwards.
Okay, you go backwards, and then there's so I mean, there's one chamber with the infinite factor, and then there's another chamber where there's just finitely many factors. So if you go from there to there, you need to glue as you pass through the ray with the infinite d0.
Right. So in this paper with Pietro Longhi, we discuss something about how to go from there to there. But that was just at the level of some speculation at the level of character. We didn't really implement it at the level of the algebra. So yeah, so this is given by I think the 2000 or 6 or 5, I don't remember. So with Dima, Galikov, and Masahito Yamazaki. So this is 19. So after this other basis, I just haven't go back and look at this gluing basis. But I keep thinking maybe there's some keyword application for that as well. But I'm not sure.
Okay, I think we should finish to be able so that I can set up Dima's talk. So thank you very much.
Yeah, thank you.